Hello everyone, welcome to our FPGA design course with VSGL. In this video, we will give you a little brief about what we are going to cover in this learning series. By the end of this course, you will be able to design your complex FPGA projects with confidence using VSGL. So let's dive in and start mastering this language together. Throughout this course, we will work on the variety of projects and practical exercises to develop the deep understanding of VSGL and FPGA. We will begin with the straightforward projects and then gradually increase the complexity of our projects to design bigger systems. To test these projects, we will use the Cyclone 2 development boot for the experiment with the real hardware. In this course, we will cover the essential topics such as signals, constant, generics, variables, and many more things. These are fundamental concepts that form the basic building blocks of VSDL. We will explore the various data types in VSGL and learn how to create the custom data types as well. Additionally, we will go into the type conversions. This feature will enable us to convert the data between different data types. We will use the typecasting functions and VSGL functions to convert between different data types. After that, we will learn about the VSGL operators. There are around 30 VSGL operators and we will cover each one in details later. Next, we will explore the process and block statements in VSGL. We will cover both the registered version and the combinational version of these statements, including the sensitivity list. You will learn that how to determine which signals should include in the sensitivity list. We will also discuss the general structure of the VSGL files. We will cover the entity declaration, the architecture declaration, and the overall structure of VSGL files. Additionally, we will learn how to instantiate components and create the structural designs. We will discuss nearly all the VSGL keywords, including both concurrent and sequential statements. Lastly, we will explore the functions and procedures which are useful for performing the actions that need to be repeated multiple times. We will also explore the VSGL libraries and packages, both existing ones and how to create your own. Throughout this course, we will use the numerous example to demonstrate how to apply VSGL concepts in various scenarios. These examples will demonstrate the use of specific keywords and the options available when we are using them. Next, we will be creating the full designs including finite state machines, shift registers, serializers, memory components such as RAM, ROMs, etc., multiplexers, tri-state drivers, comparators, etc. We will walk through these examples step by step. Additionally, we will talk about several FPGA projects that we will implement and load onto the FPGA development board. This hands-on approach allows us to test our code in real hardware and interact with it to ensure that our FPGA designs functions as expected. Our first project will involve reading the input from a single switch and controlling a single LED output. This project is focused on understanding the tools and procedures required to implement a project and program the FPGA on board. Next, we will implement a simple state machine on the FPGA development board. This example will demonstrate that how the state machines can be implemented and run on the real hardware. Next, we will tackle a slightly more complex topics, which is how to synchronize the asynchronous input. We will focus on debouncing a switch input and discuss the approach how to achieve this. We will explore that how to generate a PWM pulse width modulation signal using an FPGA. We will cover a simple method for generating pulses, including how to vary the period and adjust the duty cycle of it. Next, we will dive into designing a shift register on the FPGA development board. This topic adds a bit more complexity to our project. We will develop a 4-digit 7-segment display on the board to show a number that corresponds to how many times the switch has been pressed. This project adds a practical aspect by interacting with the boards and its components, and it will add a hands-on element to our learning experiences. Lastly, we will develop a communication module, a UART, Universal Asynchronous Receiver Transmitter module. This module will work alongside the state machine and enable the communication between the FPGA development board and a computer over the RS-232 interface. We will make the extensive use of Intel Quartus software in this course. We will use it to create and compile our FPGA projects as well as performing the pin assignments. Pin assignment is the tool which involves mapping ports in a VHDL file to the physical pin on the FPGA device itself. Pin assignment is the process of mapping ports in our VHDL code to the physical pin of the FPGA device. This step is crucial for ensuring that our designs functions correctly on the actual hardware. I will walk you through how to perform this in this course. I will also give you a basic understanding of how to use the Quartus IP catalog. This catalog contains pre-designed VHDL components that you can select, drag and drop into your VHDL project. This feature simplifies the designer's life because most of the work has already been done in these catalogs. All you need to do is just learn how to generate these IP designs and then incorporate them into your own projects. I will provide an example to show you how to use Quartus IP catalog in this learning series. Additionally, I will demonstrate how to use the USB Blaster to program the FPGA. This is particularly useful for testing purpose right after compiling your projects on the development board. We will also explore some of the output reports of the Quartus packages, including the netlist viewer. This tool is quite useful because it allows you to see the hardware realization in your design. When you write your VHDL code, it exists in the text editor. However, on the physical device, it's implemented using the registers, combination logic, and gates such as AND gate, OR gate, NOT gate, etc. And all these things are connected by some wiring, right? The netlist viewer provides a visual representation of this hardware realization, helping you to understand how the physical hardware performs the functions, which you are describing into the VHDL. We will also explore the fitter reports, which is the another type of report provided by Quartus. This report is valuable for understanding the resource consumed by your VHDL design. It provides the detailed information about the allocation of the resources on the FPGA and giving you the insights into how efficiently your design is using the available hardware. You will be able to see that how many registers and gates your design uses among all other things. This report gives you a comprehensive overview of the resource uses and help you identify where the resources are being utilized. We will also explore the Quartus assignment editor. This tool allows you to fine-tune the implementation of your design. While your VHDL code describes the behavior of your design, the assignment editor helps you to optimize how that code is translated into the physical hardware by the Quartus compilation process. We will also explore the other settings, options, and optimizations available within the Quartus. Additionally, I will provide a basic introduction on the timing analyzer and how to create a basic timing constraints, including generating an SDC file. However, this coverage will be introductory. For verification and simulation, we will be using ModelSim. I will demonstrate that how to create and compile ModelSim projects, write module label and system label test bench models, and use text files to generate inputs and output vectors for testing. By using the assignment editor, you can influence how a specific section of your code or design are implemented in the hardware. This optimization can lead to better overall design efficiency. Understanding how to test a complex FPGA design is very crucial. We will cover that how to perform the simulations using ModelSim, including developing the comprehensive test benches, especially for the final project. We will write the test benches at the module level for the various modules and ultimately design a system level test bench to ensure the entire system functions correctly when all the models and all the modules are integrated. We will use the wave window in ModelSim to analyze our results and ensure that they are aligned with our expectations. This approach ensures that our FPGA designs are thoroughly tested and functions as intended. This FPGA development board with the Cyclone 2 device looks great. It has 7-segment display which will definitely come in handy for our projects. It seems like a very capable board for learning and experimenting with FPGA design in budget. You can also try the mid-range FPGA devices as well, like Cyclone 4 devices, etc. The other thing that is highly useful about this development board is that it has these header pins. These general purpose input-output headers on the board let you easily connect other hardwares on the FPGA for experiments. This flexibility is great for trying our new ideas. This is quite useful if you want to experiment by plugging in other hardware modules onto your FPGA development board. There are also an LCD connector at the side, which means you can connect and control an external LCD device with this FPGA. This summarizes what we will cover in this course, giving you a good understanding of FPGA designs. Hope you are looking forward to it. In the next session, I will show you the easiest way to grab the Quartus Prime software for free to practice the exercises of this course. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.